Okay, up to now we've been kind of analyzing oscillatory motion by looking at horizontal springs or springs with a mass attached to them that are oscillating horizontally, and for realistic reasons, maybe on a or semi-realistic reasons on a frictionless surface, so that the only force applied to them is the force of the spring. Okay, and we came up with our functions where we have a displacement as a function of time is equal to the amplitude times cosine of an omega t plus phase constant. Well, what if we have other forces acting on them? So let's take the case where instead we have a spring and a mass hanging vertically from a ceiling or some rigid support. Okay. Now in this case, gravity is also acting, but gravity is constant, and because of that, it allows some really nice results. So let's take a look at this case. So if you take this mass and you hook it to the spring and hook the spring to the ceiling and then lower it gently so that it just leaves your palm and doesn't oscillate. It's just sitting there. Okay, so it's stretched some amount we can call delta S 0. Okay, but it's not moving because the force of gravity is offsetting this frictional or this spring force. Okay, so we have mg pulling down. Whereas before we only had the spring force, which would cause it to pull back to the equilibrium spot. All right, well, let's go ahead and analyze that with Newton's second law. So we've got Fs minus mg is equal to F net, and F net through Newton's second law is equal to ma, but it's not accelerating, therefore the net force is 0. Therefore our frictional force, which is k delta S 0 in this case, must equal mg. Okay, so let's hold that result here, and now let's analyze a fuller description. So let's analyze this right here. We have a spring, the same spring, same mass, but we pull it so that when we let go, it'll be pulled upward with a net force. Now that net force, so we've pulled it now a distance we'll call delta S, true delta S. And that's from the same equilibrium point. All right? So this time we have a force of a spring and minus mg equals ma, but a is not 0 this time. So we have k delta S minus mg equals ma. All right. But if we use this result in here, we can say k delta S minus k delta S 0 equals ma. And factor out the k, we have delta S minus delta S 0 equals ma. Well, that sure looks like this scenario here. If I take this spring, okay, and assume that the position where it hung without moving, if I take that as my new equilibrium point, okay, so I measured from that point, well, that is the same as the new displacement. So this displacement I'll call delta S prime gives me this equation. So delta S minus delta S 0 equals ma. We can call that delta S prime. So that's just the difference between the true delta S and then delta S minus that initial stretch equals ma. But that's the same thing as just some frictional force or spring force, where we instead measure the equilibrium point to be the new hanging position. This equation up here was the result of this equation here. Oops. Was a result of that equation where we measure from the true equilibrium point. But this has the exact same form as long as we just measure from the new equilibrium point. And that's the beauty of having this constant force applied. All it does is shift the equilibrium point And so as long as we just measure from the new equilibrium point, all the dynamics are the same. It'll oscillate up and down about that new equilibrium point with whatever amplitude we pull beyond that equilibrium point, and have still the same cosine function.